Okay, the model that we are going to use is what we call the asymptotic-gain model, and I will present it in this session. So this represents a network blockwise. Blockwise, I will explain it. This is a source, the signal source, delivering the information that we want to process in the amplifier. And here we have a load, and we have a load quantity. The load quantity can be voltage or current, and also the source quantity can be voltage or current. That's why I just used this circle and I didn't make it a voltage source or a current source. Then we have a network, and somewhere in this network consists of all kind of, let's say, components like resistors, capacitors, whatever, and it can also be transistors or operational amplifiers. But if there is amplification involved, a small signal diagram of an amplification, of an amplifying stage, is always represented as a controlled source. So this is a controlled source. It has a controlling quantity, which is EI. It can be current or voltage, and it has a output, a quantity that is delivered, a controlled quantity, which is either also a voltage or a current. That's why I call it E. And in this thing, there exists a relation. We say the controlled quantity is some gain times the controlling quantity. So it can be the gain of a transistor, but this can also be the gain of a complete operational amplifier. This can be the output voltage of the operational amplifier, and this can be the input of the operational amplifier. So that is, let's say, this model is universal for any kind of element that we use as amplifying device. Now, the network is constructed as is. Let's say there can be some transfer from this controlled quantity to the load. We call it lambda. There can be some transfer from the source to the controlling quantity. We call it kappa. There can be a direct transfer from the source quantity to the load. We call it rho. And there can be some feedback thing, like that we are having transfer from the load quantity to the input of the controller. We basically have two, what we are going to do is we are going to calculate, we are going to study the loop gain and the asymptotic gain and the ideal gain of a system with this model. And the first thing we do is we replace this one with a independent source. So we replace the controlled source with an independent source. Now, don't think this is, let's say, a very let's say this is not a special trick. This is just to break the loop. Basically, we are breaking the loop. We are saying the relation does not longer exist, but we denote it just here. And that makes it that you can say, well, assume there is so many voltage here, what will be the voltage there? And you can do nothing assume if there's a controlled source, because then there's this relation. So this mathematically breaks the loop, and enables us to later on calculate, for example, the loop gain, the gain from this source through the whole thing to the input. So we have selected a controlled source. It can be any controlled source in your circuit. And if you want, you can even model a capacitor or a resistor with a controlled source and select that one, but probably the model doesn't tell you anything then. But that will be later on, the conditions for which one you should select. So we denote this relation and we call this A the loop gain reference. Now we have the following equations. So I already explained the transfer. So we can have we have two independent sources. We have the signal source and the controlled source. And we have two responses, being the load quantity and the controlling quantity. So here you see the load quantity and the controlling quantity, and they can be written as a function of the two sources, ES and EC. And if you study how it works here, you see that this EL is rho times ES here. If the other one is 0, if EC is 0, then you can see ES here goes through rho to EL, and in this way you can explain all these terms. This one, lambda beta kappa, is like this. It is this response on this change. So it is like the product of lambda, beta, and kappa. So the loop gain reference, we still have it, and this is the definition of the terms that I just explained to you. Now let's see what is this loop gain. If there's a transfer beta, then you see there is some transfer from the controlling quantity to its own input. And basically, because there was something like it was controlled by the input, it basically tells you that there is a loop. So this closes the loop, and the product of A, lambda, beta, kappa can be seen as loop gain. And we denote it by L to have a little more compact formulas. So L is loop gain, and it is the gain enclosed in a loop. And people call it open loop gain, but you see the loop is closed. So it is the gain enclosed in the loop, and you calculate it by making the loop open. So it can be written as this. You calculate it from the product of A, this one, and the response EI due to a change of EC, this one. And later on, I hope to have time for an example. I think I will have time because this is going quite quickly. So negative feedback means that the loop gain is smaller than unity, is negative. That would be corrected. So a positive change of this one would result in a negative change of this one, would correct this one. If this one would be too large, then this one would control it and make it smaller again. That is how negative feedback or corrective feedback works. So then we can write down the source to load transfer, knowing all this stuff. We can say the source to load transfer is EL over ES, and you can just use this model and calculate from the previous, from this matrix equation and the loop gain reference, you can calculate that the source to load transfer will be given by this. And then we substitute A lambda beta kappa equals L, and then you find something like this. Rho minus 1 over beta minus L divided by 1 minus L. That is the source to load transfer. And an interesting thing is that we might ask ourselves, what will happen if the loop gain goes to infinity? Because that was in the model of Black, you remember that the controller became the ideal controller. It had an infinite gain, so we suddenly have a null-wise controller, so we have the ideal gain. And that is what you do. You define the asymptotic gain as the gain when the loop gain reference approaches infinity. So the gain of this stuff goes to infinity. Then we have the asymptotic gain, and we substitute, so we calculate it. This is easy to calculate from the previous expression. And then we substitute this back in the source to load transfer. And if you do so, you get this expression. You see that the gain with feedback A index F equals the asymptotic gain times minus L divided by 1 minus L plus rho divided by 1 minus L. Now, can we say something about this expression? I hope so, otherwise this was all for nothing. So this is the asymptotic gain, this is loop gain, direct transfer. Now, let's see the direct transfer. Direct transfer was the transfer from source to load if this reference variable was set to 0. Basically, it says, if the amplifier is dead, if your amplifying device has no amplification anymore, there are still transfer from source to load. But imagine that if that is the case, and this transfer would already be equal to the gain you wanted to have, then probably you didn't need an amplifier. So in many cases, rho will already be much smaller than your asymptotic gain. Or let's say the ideal gain, the gain that you wanted. And what we also saw is we want to have a good controller. We want to have a good copy of the source signal and an accurate amplifier. So we want to have a high loop gain, which means L is minus a lot. So there is here 1 plus a lot, which means that rho divided by this number can almost always be ignored. And our expression is simplified in this way. And this looks like black, but you didn't see me make any assumptions. Not for the load impedance, not for the feedback network, no common mode reaction, nothing. So it looks like black, but it is more complete. It is equal to black if there's no direct transfer, if kappa equals 1, if lambda equals 1, and then if beta is 1 over this k, which is used in a model of black. So in a two-step design, because that is what it was all about, we wanted to have a two-step design. We first designed the ideal gain. Now I have to make you believe that we can replace this asymptotic gain with ideal gain, because remember, the asymptotic gain was not defined as the ideal gain. The asymptotic gain was defined as the gain when the loop gain reference goes to infinity, the gain of the loop gain reference. So the conclusion is, so here we want to have this, but here is asymptotic gain and here is ideal gain, and they are not yet, per definition, they are not equal. So gain, ideal gain, loop gain, and we call this servo function. So if we, and this will be the next presentation, select the reference variable in a proper way, then we can find conditions under which the asymptotic gain will be equal to the ideal gain. I must warn you, it seldom happens. There's always a little error. But in the frequency range, in the operating range of interest of our amplifier, we can almost always make it true. And with SliCap, we can check it. Because in SliCap, and that is what the gain type is about in SliCap, we can calculate the asymptotic gain, the loop gain, the direct transfer of an amplifier and the servo function of a negative feedback amplifier and plot it and see if the asymptotic gain equals the ideal gain as a check. So this was the presentation of the asymptotic gain model. The next one will be about the selection of the reference variable.